Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing?
Good.
Good? Yeah, hanging in there? It's good?
Trying to stay focused.
Yeah, I think that's that's definitely a hard thing. I mean, so many big changes to, our lifestyles. It's hard to stay focused during this time. So, just do your best to hang in there and, we'll come out the other side of this. That's for sure. Okay, so the plan for today is just like we promised on Monday, I'm going to go over the new starter code for the project for you. So what I did yesterday was I spent some time and I overhauled the starter code to basically fill in some more stuff for you guys. So there's less development that you guys have to do and more just kind of filling in the blanks. So I kind of structured the starter code kind of similar to kind of the very first MATLAB activity that we did at the beginning of the semester, if you can remember that. So basically now the way that I've formatted it, there shouldn't be any additional code that you have to write, but you do kind of have to fill in some parts that are like redacted basically. So it's kind of mostly just fill in the blank. So most of it's there for you. But what I wanted you guys to focus on was developing the coefficients of the equations that we've been doing basically all this time. So today I'm going to go over the finite difference starter code. So if you want to do the project with that, then you should be good to go from this. But if you want to do it with finite volumes, or if you're a graduate student where you have to do both finite difference and finite volumes, I posted the starter code for that already, but probably we'll wait till we get through some more finite volume stuff before we go over the code together in class. So if you if you can, I would get started with the finite difference, and then as we cover more finite volume stuff, we'll go over that together in class. Okay? And then besides that, I've updated the project requirements a little bit, so I want to go over that together with you. And I posted a template for the final report that I want you guys to use too. So basically just have to fill in the sections that I outlined in the final report template. Okay? And then after that, the plan is to go start covering convection with finite volume. So kind of, we're progressing along the same path that we went over finite difference. So after diffusion comes convection. So we'll start with that today. Okay. Before we get started with any of that, are there any questions that I can answer before we get started?
Sorry, really quick. So this code is going to be our project?
Yeah. So this is posted
Okay.
on Titanium. So this is posted on week 12. So basically, you would download this code and then you would kind of fill in the parts that we'll go over together in class. Fill in the parts where I basically say insert here. So then you would fill in the code there, and then then that's what you would use for the project. Okay. Oh yeah. So also remember that homework 5 is due on Monday. So so make sure you're doing that because that'll help you out with the midterm as well. So basically after you guys turn in homework 5 on Monday, I'll post a solution so you'll have that to study for the midterm exam. Okay.
So are we going to be going over the starter code for the final project or for problem 3 on homework 5?
For the final project, we're going over the starter code for the final project.
Okay.
All right, so there's no more questions, then let's go ahead and get started. So here's the starter code. So I've named it starter code 2. So if you want to work off the original starter code and you've kind of already worked with that, you can go ahead and keep doing that. But this is kind of the updated versions where I basically just copied and pasted my own solution and I just kind of redacted some of the parts of the code. Okay. Okay, so let's start with section 1 up here. So section 1, just like normal, this is where we define all the variables in our for our problem. So we have the length of the domain, we have the number of grid points in the x and the y direction, we have nx and y. Then we have the grid spacing, dx, dy. Visc here, remember Visc here, this is our diffusion coefficient. So in this case, you can see my diffusion is pretty low, so it's 0.0001. So this is the low diffusion case. Here we have our time step size, and here we have the number of time steps. Okay. So one decision that I made for you guys for the final project where originally I gave you guys the option of either using an explicit Euler or implicit Euler time advancement. I've already made that decision for you. So this project kind of works a bit better, or you spend less time waiting for the code when you run a implicit solution. Because if you run an explicit solution, in order for it to be stable, you have to make the time step size really, really, really small. You know, to kind of save you some time, I increase the time step size here. Okay? Because with implicit time advance, remember, we always get a stable solution. So we're free to kind of choose the time step size to be something that's kind of convenient. So I picked this time step size here to be kind of basically to give us kind of the nicest video possible afterwards. And then after that, I defined these parameters here. So if you remember from the project specs, the whole purpose of the project is to simulate this ring. So originally we have a ring of some quantity that's going to be you know, that's going to form our initial conditions. So we have to define the center of that ring. So our center is going to be at 0.5 and 0.25, and then the radius is going to be 0.2. So I can bring up the project document. Let me do that. Okay. So this is the ring that I basically am specifying here. So you can see that we have this ring of basically yellow in our solution here, where that's going to define you know, our initial condition. So what I define in that first part of the code is the location, so the XY coordinates of that, and also the radius of this ring. Okay. Okay. And then we compute our left-hand side matrix, or we just create a variable for it. So we have we call our left-hand side matrix A, just like we normally do, and it's a zeros matrix, and it's n total by n total. And then we create the right-hand side vector B, and that's an n total by 1 vector. Okay. So most of it's pretty standard stuff here. So the only things is that, you know, you have, since it's an unsteady problem, you have to define the time stepping parameters, which is the time step size and the number of time steps. And then since we have a unique initial condition, you have to define the parameters for that too. Okay. Okay. So that's section 1. So section 2, so there's nothing that you have to do for section 1. Section 1, you can leave it alone, at least while you're developing the code. But later on, once you know, I ask you to change some of these parameters, you can go up here and choose this. So for like figure 1, when I asked you to change the density, the diffusion coefficient, you would change this parameter here. And then when I ask you to change the mesh density, you would change these parameters right here. So instead of 25 by 25, this is the coarse mesh. So when I ask you to do the medium mesh, then you would change this to 50 by 50 here. Okay. So there's nothing that you have to add here, but you would need to change these in order to produce the different figures that I'm asking you to do. Okay. Okay, and if you have any questions, definitely just stop me anytime. If I'm going too fast, or you want to know more about a previous line of code, then just let me know, and I'm always happy to go back to it. Okay?
Professor, for the mesh size, is there a limit that we should probably stay away from to not? I think you mentioned like we could possibly damage our computers. Yeah.
Well, not damage your computers. It would just take a really long time. So I've kind of lowered the requirements for that. So previously, the biggest mesh that I wanted you guys to do was 75 by 75, and that took that. You know, with these settings right here, that takes about 5 minutes to run. So you know, you shouldn't. That should be pretty harmless. But now that fine mesh is going to be optional because it takes my computer 5 minutes, but my laptop's a gaming laptop, so it's pretty good. So it might take your laptops a bit more time. So I don't want you guys to wait. You know, that depending on the state of your laptop, that could take up to like 15, 20 minutes. So I don't want you to wait that long for the results. So the max that you need to do to get credit is just 50 by 50. But if you want to crank it up, you can go all the way up to 100 by 100 if you want. But just kind of be prepared to run your laptop overnight if you want to do that.
Okay, that's good to know. Thank you.
Mm-hmm.
If we're doing it 100 by 100, do we get bonus points or?
I'll give you a nice handshake when we're done with this coronavirus stuff, but I can't give you any extra credit for that because that's you know, I think that's a bit unfair. If you have a computer that's good enough to run it, then you know not everyone has that. So, but it's cool. It looks cool. So if you want to run it, then you can definitely you know, enjoy the video that kind of comes out of it. Okay. So that's section 1. So now let's go to section 2. So here, section 2 is kind of where we start to need to add some code. Okay. So first of all, let's go over these two. You can see here I've defined two vectors, one called sol current, so that's the current solution, and next is sol next, so that's the next solution. So remember, whenever we're doing an unsteady problem, we need to have variables to store the solution at time is equal to n. Right? And then we also need to have a variable for the solution at time n plus 1. Okay. So right now these are just empty vectors, but we're basically going to be filling these in, as we go about the code. But we basically define those here just to kind of create the space for it. Okay. And then lines 29 and 30, you don't have to change this at all. But basically, this is just the code that I'm providing for you to make sure that it produces a video. So basically what this does is it opens a video file. And then later on, we can basically add frames to this video file. But you don't have to worry about that at all. Okay, so the next line, we are initializing our time variable. So remember, we're doing an unsteady problem. So we have to start time is equal to 0. So that's that there. Okay. And then lines 37 to 49, this is when I'm gonna start asking you guys to fill in some stuff. Okay, so you'll see this kind of code snippet here called insert here. So I put it in all caps so it's a bit easy to see. So whenever you see this part in the code, you can imagine that this is basically like a blank that I'm leaving for you. So this is basically places where I want you to fill in some code to kind of make it work. So right now there's this insert here. MATLAB will think it's some variable, but it's not defined. I didn't give it a variable. So if you try to run this code right now, MATLAB will give you an error because this insert here is not defined at all. So everywhere, so in order to get your code to run, you have to fill in everything that says insert here. Okay? So the first thing I want you to do is to fill in the initial condition. So remember, the initial condition is given by that ring that I showed you previously. So there's a formula in the project specs that I gave you. So it's given by this formula right here. So let me bring up the code. Yeah, this one right here. So our initial solution here at phi, which is phi at time is equal to 0 is equal to 1 minus square root of x minus xc squared plus y minus yc squared minus big R. Okay. So basically, what I want you to do in that initial part of the code is implement this equation right here into the code. Okay. So I did it with 3 different lines right here. So you can basically fill in, the code here to basically allow you to do that. And if you want to do this in a different way, you're certainly welcome to do that. But this is just kind of the way that I've implemented it in my code. But basically, what you should do when you run this code and you see figure 2 pop up, figure 2 should look like this guy right here. So it should look like a ring, in your domain like that. Okay. So that's the first thing I want you to do. I want you to basically implement this code. You can basically just fill in the blanks to implement that initial condition, where you basically are just following this equation right here. Okay. Okay. So then after you fill in that code, then this next segment of code right here, this just plots the initial condition. So there's nothing you have to change here. Okay. And then from here, I basically start getting ready for the time looping. Okay. So remember, whenever you don't see an insert here, then you don't have to touch any part of that code. So that's code that's basically done for you already. Okay. Okay. So then now we enter the time loop. So here, we are looping over all of our time steps. So remember, for every unsteady problem, we have to loop over all our time steps. So here I've added basically a progress bar for you. So basically, when you're running your code, you can kind of see in real time how it's doing. So you're not just kind of waiting at a blank screen. So basically, at each iteration of your time loop, the MATLAB will print out something that says solving step something out of something. So when this bar is basically complete, then your solution will be done. So that's basically just to help you kind of see how your solution is progressing. Okay. Okay. So now we entered kind of the bulk of where I want what I want you to do, which is filling in the left-hand side matrix and right-hand side vector. Okay. Because in this class, what we've been doing is in the classroom we've been developing these algebraic equations based on either the finite difference or finite volume methods. And what I want you to do is I want you to take those equations and take those coefficients and basically implement them in the right locations in the matrix. Okay. Okay. So we jump into this loop. So you can see we have our typical nested for loops. We have 4i is equal to 1 or 2 to nx minus 1, and 4j is equal to 2 to ny minus 1. So this is our typical, spatial loop. So through this nested for loop, we can visit every node in our mesh. And so for each node in the mesh, that we always have to develop some kind of algebraic equation for it. Okay? So what this loop will do is will allow us to do that. Okay? So the first thing that we do, so I've already provided this code for you, is to compute the x coordinate and the y coordinate of each node in the mesh. So that's given you by x pos and y pos. Okay? And then after that, we come to the first thing that I want you to implement is to compute the x and y convection velocities. Okay? So the formulas for the x and y convection velocities are given to you in the problem specs. So let's go ahead and take a look at that. Okay? Actually, it's up here. So you can see the formulas for u, which is our x velocity here, is given by cosine of 5 over 2 pi t times sine of 2 pi y times sine squared of x times pi. And then our y velocity is equal to minus cosine of 5 over 2 pi t times sine of 2 pi x times sine squared of pi y. So basically for that part of the code, I want you to implement these two equations into code right here. Okay? So you have your time variable t up here. You have your x coordinate and the y coordinate, and then you can use the cosine and sine functions and pi within MATLAB to basically implement those functions for you. Okay. So then after that, then we start going into the left-hand side matrix. So just like we always do with our 2D problems, we have to have a section of code that computes the ID numbers. So remember, this is pretty standard stuff for any 2D problems. We have to compute the ID number for this cell, so that's always my ID. And then we compute the ID number for the left neighbor, and then the ID number for the right neighbor, and then for the upper neighbor and the down neighbor. Okay. So this next section of code, this is going to be for our higher order convection scheme. So when you're first implementing the code, you don't have to worry about this. But later on, basically after we finish convection with finite volumes, I have a lecture planned for basically higher order schemes. So when you come to this part of the code with left ID 2, right ID 2, up ID 2, down ID 2, you don't have to worry about this until we do higher order schemes. So initially, when you're first implementing the code, you can just ignore this, but we'll need it later. Okay. Okay. So then here, this section of code right here, lines 96 to 108. This is kind of the kind of the most important part that I want you to focus on. So here, what I want you to do is to fill in the coefficients for each of the different neighboring nodes. So up, right, left, up, down, and my ID. Okay, and I want you to fill in the coefficients that are due to diffusion, and then also the coefficients due to convection. Okay, so I want to do it in two different steps. But if you want to combine these steps, you're welcome to do that. But I kind of break them apart just to kind of make things easier later when we do the higher order stuff. And so I've left a lot of these blank, but I did fill in one for you just so you can see. So I filled in all the coefficients for the right neighbor. So for the right neighbor, you can see due to diffusion, you get minus k times dt divided by dx squared. And then for convection, you see we subtract a u times dt divided by 2 dx. Okay? So if you look into your notes, basically when we did 2D diffusion problems, 2D convection diffusion, which were unsteady, you should be able to match up these coefficients here with what's in your notes. Okay? Excuse me. So what I want you to do after that is I want you to fill in the coefficients for the left neighbor, the up neighbor, the down neighbor, and my ID for both diffusion and convection. Okay. All right. And then for these parts right here, I want you to use kind of what I call the basic central difference scheme. So when you're first implementing the project code, I want you to use basically all the methods that we've talked about so far in the class. So when you do the higher order stuff, that comes later. Okay.
So question for the For the set diffusion coefficient base implicit Euler, that part. Our code has to look like the statement that you have in terms of like solving for that formula.
Right. So remember, when we did unsteady diffusion problems, and we looked at the coefficients in front of each of the neighboring phis, they had some coefficient in front of them, right? So if you look back in your notes and you look at the coefficient in front of the right neighbor for the diffusion, that was minus k dt over dx squared. Okay? So basically what I want you to do is I want you to fill in the similar coefficients for the left neighbor, the up neighbor, the down neighbor, and also my ID. Okay? And then similarly for the left ID, the up ID, and the down ID. Okay? Yeah, so check back in your notes and you should see kind of formulas that look like this. Or these coefficients here, and I want you to kind of write in or code in the analogous formulas for the other neighbors.
Okay, thank you.
Mm-hmm. Okay, so then this big block of code right here, which is commented out, don't worry about this yet. So when we come to higher order schemes, then we'll go over this. But I did the same thing here. So I gave you basically the one sample. So I basically gave you the solution for the right neighbors, which there are two in this case. So the thing with higher order schemes is that we're going to have more neighbors that we need to account for. Okay? So I gave you the coefficient for the immediate right neighbor and then also for the far right neighbor. Okay? So you can basically use these as reference and then reference these with the notes that we're going to do later on, and then you should see that these coefficients should match up. But this you don't have to worry about until after we do higher order schemes. Okay, so that's all the left-hand side matrix coefficients. And then after that, you have to set the proper values for the right-hand side forcing vector B. So I want you to fill in the proper value here. Okay? So again, look back in your notes on when we did implicit Euler for 2D problems, and you should be able to come up with what should be on the right-hand side here. Okay. So that's all of the internal nodes. So then after that, before we solve our system, we have to apply boundary conditions. So you have to apply boundary conditions on each of the sides of the grid. So the left side, the top side, the right side, and the bottom. And then for this particular problem, all the boundary conditions are the same. So they're basically going to be zero flux boundary conditions. So you have a zero Neumann condition basically all around. So basically, once you figure out one of those, then you can fill in the rest. So I didn't want to fill in one for you. I didn't want to fill in one for you guys because then they're all going to look the same. So basically, but we've done zero flux boundary conditions before. So look back in your notes and look back at some of the previous examples, and you should be able to fill this in, basically copy and paste. Okay, and then after that, after you define the boundary conditions, I want you to compute the solution at the next time step. So for implicit Euler, there's it's a very short line of code, but it's a very important one that I want you to fill in here. So basically at this point, our left-hand side matrix and right-hand side vector are fully defined. So our left-hand side matrix and right-hand side vector are fully defined. So I want you to use those to compute the solution at the next time step. Okay. And then once you do that, then on this line right here, I want you to update the current solution. Okay. All right. Okay. So that's, that's, if you look back to some of the previous notes where we did unsteady problems with implicit Euler in 2D, you should be able to kind of see, what you should need to fill in here. Okay. And then after that, then I have this section of code here to basically produce the video. So you don't have to change this at all. So this is, you just leave this alone. Oh, this is not every 50 time step. This is actually every time step. Okay. Just a minor typo in the comment. And then the last thing that I want you to do is I want you to update the time variable, because every time we run the this loop, each time we enter a new iteration of the loop, time is going to advance by a certain amount. Okay? So then I want you to write in the code to update the time variable to whatever the new value is based on that. Okay? And then that's it. So then after that, then the MATLAB code will tell you how long your solution will run, and then you should have a video. So that's the new starter code. So the new starter code, you basically mostly you're just going to have to fill in the blanks over here. And I've left you a couple examples to basically help you out. So hopefully this will be a bit easier to work with than the previous starter code, where there was kind of a lot of stuff that you needed to develop. So this is basically my solution. I just took out some lines from it. Okay. Any questions on the starter code?
Yeah. So you said for the higher order to leave it blank. So are we just going to fill in what we know now, and then by the time the project's due, we're going to have to implement that?
Yeah. So we haven't gone over higher order schemes yet, so you don't have the information to fill this in. But basically, what's going to happen is that you can either choose the basic scheme. So this is these lines right here, 105 to 108. This is kind of like the basic convection scheme. So this is kind of the one that we've been using, all the way up to this point. So when you implement the higher order schemes, what you're going to do is you're going to comment these lines of code out, okay? Because we don't want the basic scheme, so we basically tell that to go away, and then we uncomment all of these. Okay. So when you do convection, it's an either/or thing. So you either do the basic scheme, or you do the higher order scheme. So you never do both at the same time. So to start, what I want you to do is to start with the basic scheme. Because this is kind of the scheme that we've been using in this class up to this point. And then once you get this working, you can comment it out, and then you can uncomment the higher order scheme. Okay. But that's not going to come until later on, because we need to actually learn higher order schemes before we can implement it. Okay.
What was the keyboard shortcuts for you to comment everything out?
And
then,
yeah, so to comment everything, you highlight the lines of code that you want. You do Control-R. And then to uncomment it, you highlight all those lines and do Control-T. Yeah, very useful keyboard shortcut. Mm-hmm.
Control-R to comment, and then Control-T to uncomment?
Yep. Mm-hmm. Okay. Any other questions on the starter code?
Yeah, Professor, I think around line 50, go right there, the X, yeah, 43 and 40 to 45.
Okay. Mm-hmm.
Now, the one equation you had for phi, it had the variables X, Y, and I believe R inside of it. Are we supposed to just, you see what I mean by that one equation? Do you want us to get that equation and implement it, or we separate it 3 times, or?
So that's so that phi, this one right here, this phi right here will be your Sol cur. Okay, so the ending equation here, Sol cur and my ID, is going to be this. So basically, I use 3 helper variables to kind of do that, but you can kind of implement this how you want. So the XC and the YC and the big R, so those are already given to you. So those were defined up here. So this X center here corresponds to XC in that equation. The Y center corresponds to YC, and then the radius right here, this is big R. So basically, you can use this code if you want, but if you have if you kind of want to write it all in one line, that's totally fine too. So you can write it all basically in one line to implement this formula, because you have this X pos here. This is the same as X in that equation. Y pos is the same as Y. Okay. So you have X, you have Y, you have XC, you have YC, and you have big R. So then you can basically implement that equation here. So it might actually be simple to implement it in one line. But I think the reason I did this is because that line got kind of way too long. So it kind of got like kind of way out here. So I kind of separated it out to up there. But if you want to do it all in one line, that might be easier for you to do too.
Yeah, can you go back to the paper or
Sure.
the project requirements?
Mm-hmm.
So right here, when we see a phi of X, Y, and Z, so theoretically that X diff and Y diff, we're gonna plug it into here and write it out into an equation, right?
Yeah.
Or,
mm-hmm.
Okay. But you have an equal sign next to them. That's the only part where I'm a little confused.
Oh, which one? I mean this equal sign right here?
And in the MATLAB code, like X.
Yeah, so, right. So basically what I did.
X by itself is an X diff or X pos, right? That should be X position.
Right. So actually, let me kind of tell you kind of what I did here. So X diff, I basically defined that as this guy right here. So I said that X diff was X pos minus X center. And then Y diff was Y pos minus Y center. So that's basically these guys right here. And then R diff, what that was basically this entire expression right here. So the square root.
I see what you did. You just got that into one variable.
Yeah. Right.
Makes sense. Makes sense.
Yeah.
Okay.
Yeah. So you can do it that way, or you can do it all in one line. You know, whichever kind of makes the most sense to you.
Yeah, I was looking at it and I was like, wait a minute, I don't know.
Yeah, I redacted that part early, but yeah, if you're not inside my brain, then that is a little bit confusing.
Yeah, it's all good. No, I understand. Thank you.
Mm-hmm. All right. Any more questions on the starter code? Okay. So hopefully that helps you guys out. So let's go over just quickly the changes to the project specs. So I didn't change too much. The biggest thing was I took away that define mesh. Okay. So let's go down to the deliverables. So the deliverables, you know, the big thing is I want you to produce the solution plots. Okay. So part one of the deliverables, this is not changed. So I basically want you to run the code 3 different times on the medium mesh. So you set nx to equal to 50 and ny is equal to 50. And I want you to run it with different diffusion coefficients. Okay? So the first time I want you to run with visc equal to 0.0001. So you run the solution and you get the video and you can save it somewhere else. Then you run the same, then you run it again and you just change vis to 0.001. Okay? And then after that, you run it, you save the results, save it somewhere else, and then you run the solution again with visc equal to 0.01. Okay? So once you got your code running, then this is pretty simple to do. So you're just changing one variable and you're just hitting run, save the results, change the variable, hit run, and then save the results. Okay. Okay. So deliverable 2, this was changed a bit. So before, what I wanted you to do was to run the code with 3 different mesh densities. So first on the coarse mesh of 25 by 25, next on the medium mesh of 50 by 50, then on a fine mesh of 75 by 75. But since you know, this fine mesh can take quite a while to run, I'm saying that the fine mesh is not required for credit. So the only thing that you have to do is you have to run up to 50 by 50. So hopefully that doesn't take too long for you guys to run. Okay? But if you want to run it on the fine mesh, you're certainly welcome to do so. But my same warning applies. So, you know, before you run it on the fine mesh, make absolutely sure that things are working on the coarse mesh, because this will take you a long time to run, depending on your computer. Okay? And you can feel free to crank this up as much as you want. So I did 100 by 100. So actually all the images that I showed here on the document, these are with 100 by 100. So I basically ran this overnight. But you know, that's kind of the limit on what you can do. Okay. So deliverable 3, this was changed a little bit. So deliverable 3, what I want you to do is compare the results when you use the basic kind of a central difference scheme that we talked about versus the higher order scheme, which is what we'll do later. Okay. So before, what I wanted you to do was to take a screenshot of the solution, basically when it's at maximum mixing. So basically when the solution looks like this. So it'll only look like this with the higher order scheme. But now, you know, all I want you to do is basically just kind of describe in words kind of what you're seeing as the difference. So if you compare the videos between your basic scheme and your higher order scheme, it should be kind of very obvious kind of what the differences are. So I want you to just kind of describe in words what you're seeing there. Okay. And then for deliverable 4, so this is only if you're taking the class for graduate credit. So if you're taking it for graduate credit, you have to implement both the finite difference and the finite volume solution. And I basically just want you to compare your results. So that hasn't changed. Okay. So those are most of the things that changed. So the other thing that I provided for you guys is a template. So this is a template for your final report. So basically, you know, you basically just have to fill in the stuff. So you can give your project a title, so you can be creative. So don't just use the same title I use. You know, give it something different. Okay. So then you write your name. I've already filled in your affiliation for you because you're all part of the mechanical engineering department at Cal State Fullerton. Okay. And then for here, you can basically fill in all the different sections. So I basically gave you a small blurb as to what I'm expecting. So you have to write an introduction section. You have to write a methodology section where you describe your methods. And I want you to at least use a couple equations. Okay. And then the results, I basically want you to talk about all the plots that I told you about. So I basically left you placeholders for all the plots. So this is figure 1. So this is comparison of the results for different coefficients. So these are all the same image, but this is basically how I want you to format it. So yours will look different because you'll have 3 images that look different, but I just put a placeholder image there for you. Okay. Next, you have the comparison of different mesh densities, again with placeholder images. Okay. And then this is, if you're doing it for graduate credit, this is comparison of the finite difference and finite volume. Okay. And then you have your conclusions, and then I have some additional instructions here for if you're going to include some additional figures. Okay. Okay. So all of that's on Titanium. So all of that should be there for you. So go ahead and check it out. And if you definitely, if you have any questions, then let me know. Okay. So are there any final questions on the project?
I have one question in regards to the methodology.
Okay.
That's kind of like a theory section where you implement your equations.
Yeah.
There's a lot of equations going on here. You're saying a couple would be fine to kind of get the point across?
Yeah. Yeah. So I want you to do at least 2. So I want you to to choose. So like you said, there's a lot of equations that are going on, but I want you to kind of pick at least the 2 most important equations that you think would get the point across. Because the way I want you guys to write this report is, you're basically going to be explaining, what you've been doing in this semester to one of your friends that aren't taking the class. So you need to include enough detail in the methodology section that, someone else that's reading your report can understand what's going on. Okay. All right, so oh, can you say it again?
Oh, sorry, I said it makes sense. Thank you.
Okay. All right, so we have a question from the chat. So how do we take a screenshot at the final time step? So that'll be produced automatically. So when you run the code, basically figure 1 will be, and your code finishes, figure 1 will have the final screenshot. So you can basically just either take a screen grab of that, or you can click on the MATLAB figure and then just save it as a JPEG and then, or a PNG, and then just import that into your report. Okay. Any more questions? Okay. So that's the final project. Definitely, I would get started on it. And definitely let me know any troubles that you have. Okay. Okay. So let's get back to finite volumes. So let me pull up the notes. So last time we basically finished up finite volumes with for diffusion problems. So the next thing that we're going to do is going to do finite volumes for convection problems, okay? Or both convection and diffusion. Okay. All right, so pull up the whiteboard. Okay. So here we're going to start convection with finite volumes. So kind of the next step in our development here. So basically what we're going to be doing for the rest of the semester is we're going to do convection with finite volumes, and then we're going to do unsteady problems with finite volumes too. Okay. Okay. So let's start with convection. So the convection equation that we're going to start with is given by this. Okay. So here I've written the convection equation in vector form. So here we have our convection term. Right. Here we have our diffusion term. and here we have our source. Okay, and then the kind of the most important guy in the convection equation, or the convection part, is this V, where this V right here, this is our convection velocity. Because remember what convection represents. So remember, convection represents an active transport of a material through some moving fluid. Okay? Okay. And so the key here is moving. So if you have a fluid that's moving, then it needs to have some velocity. So that fluid velocity is captured by that convection velocity, which I've highlighted in blue. Okay. So if you have some kind of cloud of material, okay, and you have some you can say wind or water kind of blowing through it, okay, then by convection, what's going to happen is that the convection velocities are going to push that cloud of material over here. Okay, so this is transport via convection. So remember, this is physically, it's different than diffusion, where diffusion represents, remember, passive spreading of some material kind of in all directions. Convection is an active transport where the transport happens in one clear direction, and that direction is denoted by the convection velocity. Okay, right. So, are there any questions on this before I wipe the board? Okay. Okay, so let's talk about some engineering applications where convection might be important. Okay. So the first one could be related to kind of atmospheric winds or environmental engineering, where you can use, where convection is used to model the transport of some pollutant through the atmosphere. Okay. So weather modelers use this all the time. So if they want to basically track the movement of a cloud, you can say. So the cloud is going to be pushed along through the atmosphere by winds, and that process is basically governed by convection. Okay. Right. So we can also think of a heat transfer example. So if you have a heat exchanger, then heat is going to transport through the pipes of that heat exchanger through convection. Okay. Okay. Right. So another, more, kind of an everyday example where, if you have a coffee in the morning, or even, your tea, you put sugar or milk in your tea or coffee, and you mix it around with the stir, then the kind of the mixing or the transport of that sugar or that milk is also governed by convection. And any kind of HVAC system, convection is going to be important, just because you have heat and mass and stuff like that being transported through basically through flowing fluid. Okay. So convection is prevalent basically, you know, anywhere. So if you're doing any kind of professional work with fluids or with heat, you know, convection is something that will be kind of very, you know, very well known to you. Okay. Okay. And just like we mentioned before, kind of the big distinguishing characteristic between convection versus diffusion is that convection there's a very clear direction in which it wants to go. Okay. And then that direction will drive our, you know, our numerics. Okay. Because if you remember when we did convection with finite differences, what can happen sometimes if you're not careful is that your solution can be unstable. Okay. So we had to kind of be careful how we did our stuff. So if we used if you remember, if we used a central difference scheme to model our convection derivative, then we had to make sure our grid was fine enough such that the Peclet number was less than 2. Okay. So we had that Peclet number kind of a constraint that we had to deal with. Or the other thing that we did was, instead of using a central difference scheme, we used a upwinding scheme. Either that can either be a backward difference or a forward difference, depending on which direction the convection velocity was doing. Okay. So even though we developed all those ideas for finite differences, you know, there's going to be analogous kind of situations for finite volumes. So I want you guys to kind of keep those in mind as we kind of develop the equations for finite volumes for convection. Okay. Okay. Any questions on this before I wipe the board? Okay. Okay. So just like we always do, let's start with one-dimensional problems, and then once we kind of get that down, then we can go to 2D. Okay. So we'll do 1D, convection diffusion. With FVM. Okay. So let's write out the equation. So the equation for 1D FVM is given by this. So first we have our convective terms. We have d dx of u of phi, the u times phi, minus k d dx of d phi dx is equal to q of x. Okay. So if you notice, you know, this is a little bit of a different form than how we usually write convection problems. But I wrote it in this form just so that when we take the integral, like we usually do with finite volumes, it comes out a little bit easier. So kind of the assumption that we make when we do this form is that we assume the fluid is incompressible.
Professor, is that a lambda?
It should be an x.
First term. Okay, sorry.
Yeah.
They're all x's.
Yeah, I bought a new stylus because my old one broke because it was a cheap piece of crap. So I'm still getting used to this this new stylus. So this one slides a lot easier on my iPad. So it's I'm still kind of getting used to it a bit. All right. So an incompressible fluid, if you remember from your fluids class, basically we say that du dx is equal to 0. Oh, I see what you mean. Yeah, this this first one is an x right here.
You get reimbursed for the money you put in for having to teach out of campus.
No, just because you know, if we they don't like reimbursing, so they want us to use the department funds, but that takes like weeks. And like I have weeks. You know, I had to give a lecture this evening, so I'm probably gonna keep this stylus and probably give it to my sister because she's an artist and she likes to draw on her iPad. So so I'll give it to her for Christmas or something.
Oh, that's nice.
Okay. So now that we have it like that, let's let's integrate, because remember with the finite volume solution, we're in order to develop our equations, we have to integrate this over the cell. Okay. So if we have a one-dimensional kind of grid like this, and we have our cell, which is given by this. Okay. So on the left side of the cell, we have the coordinate XL, and on the right side of the cell, we have the coordinate XR. Okay. So what we're going to do is we're going to integrate this equation from XL to XR. Okay. Okay. So let's go ahead and do that. So we could do, we have 3 different terms here. So we're going to have 3 different integrals. We have integral from XL to XR of d dx dx of u phi times dx, okay, minus k. K is a constant, so we're going to bring it out of the integral of xl xr of d dx of d phi dx dx is equal to integral from xl to xr of q of x dx. Okay. So just like we did with the diffusion problems, we're just integrating our governing equation over the over a cell. And for a one-dimensional case, we just have a one-dimensional integral, basically from the left side of the cell to the right. So that's what we integrate from XL to XR. Okay. Okay. So then now we're gonna basically apply our integration techniques. Okay. So for these guys on the left here, what we're going to do is we're going to apply our divergence theorem. And then for the source term integral, we're going to integrate that the same as we did before, where we're just going to just straight up use trapezoidal rule. Okay. And then we'll kind of see how that forms. Okay. Okay. Any questions on this board before I wipe it? Okay. Okay, so if we apply the divergence theorem on the first integral, what we're going to get is something like this. Okay, so we're going to get u and phi evaluated at the right face minus u times phi evaluated at the left face, okay, minus k, right? So this is our diffusion integral. So this is the same as what we did previously. So we have d phi dx evaluated at the right side minus d phi dx evaluated at the left side. Okay, and then all this is equal to q at xc times xr minus xl. Okay. Remember, on the right-hand side, we just straight up used a trapezoidal rule, where we evaluate our integrand q at the centroid. So we evaluate q at xc, and then we multiply it by the length of our integration, which is just xr minus xl. Okay. So this guy right here, xr minus xl, this will just turn into the grid spacing delta x. Okay, so let's continue working this. So what we have on the left-hand side of this equation is u times phi evaluated at the right face and u times phi evaluated at the left. and on the right, and on the diffusive term, you have d phi dx and d phi dx evaluated at the left and the right. So remember, these are evaluated at the nodes of the cell. Okay. So remember, we don't want that because remember, for the finite volume method, we want to evaluate things in terms of the cell center values. Okay, so we want to put this in terms of cell center values. Okay, and so to do that, we're going to do this. So let me draw a line here. So let me draw the boundaries. Okay. Okay. So these dots right here, these are going to represent the boundaries of our cell. So this will be XL, okay, and this will be XR. Okay. Okay. And then the X is what they're going to represent. Are going to be the cell-centered values for the cell of, our current cell, which is phi sub c, and then the cell-centered values for the left cell, which is phi sub l, and then the cell-centered value for the right cell, which is phi sub r. Okay? And so basically what we need to do is we need to replace the phi at xr and the phi at xl with these values. Okay? So we're going to make the same assumption that we did for diffusion, where we assume that the variation between the cells is linear. Okay? So we're going to use the following equations. Okay? So first we have phi at xr, okay, which is this one right here. So basically one way that we can express this is we can say that it's just going to be simply the average between phi sub c and phi sub big R. Okay? So we can say that this is phi sub c plus phi sub big R, all divided by 2. Okay? And then similarly, we can write out the same thing for phi at x at L. Okay? So this is going to be the average of our cell-centered value phi sub c, and the average and the and our left neighbor, which is phi sub L. Okay, so this is phi c plus phi L, all divided by 2. Okay. So to basically to approximate the face values or the values at the edges of our cell, we're just taking the average of our own cell-centered value and the value of our neighbor. Okay. Okay, and then for our diffusive terms, these are still going to be the same. So we're going to assume if there's a linear line, and then the slope in between the cell centers is going to be our values. Okay. So just like before, we have d phi dx at xr is going to be phi sub big R minus phi c divided by delta x. Okay, and then d phi dx at xl is equal to phi c minus phi l, all divided by delta x. Okay. So both of those equations basically result from the fact that we assume that there's a linear variation in between our cell centers to get those values. Okay. And what we're going to do is we're going to take these values and then plug them into this equation up here. And that'll help us get to our finite volume equation for 1D diffusion. Okay. Okay. Any questions on this before I wipe the board?
Wait.
Yeah. Quick question, or I guess Rick go first.
For the bottom right term, xc minus xl.
Oh, L. Sorry.
Okay. Just want to make sure.
Yeah.
That was my question.
Oh, okay. Yeah, that's with the messy handwriting, it's hard to tell between C and L. So yeah, thanks for clarifying. Okay. right, any more questions on this? Okay, so let's wipe the board. Okay, so we plug those in, we get the following. See, here we're going to assume u is a constant, so we're going to pull u out of the equation. Okay, so you get u times phi sub c plus phi sub r, all divided by 2, minus phi sub c minus phi, or plus phi sub l, all divided by 2, okay, minus k times phi sub r minus phi sub c, all divided by delta x, minus phi sub c minus phi sub l, all divided by delta x, okay, is equal to q at xc times delta x. Okay. So that's, we just took the expressions that I was at the bottom of the last page and just plugged them in. And so to get our finite volume equation, we can just rearrange the terms. Okay. Because we know that whenever we're developing our algebraic equations to implement in code and also to do hand problems, we always like to get them in terms of coefficients for certain terms. Okay. So let's do that. So let's first get the coefficient for our left neighbor. So for our left neighbor, our coefficient is going to be minus u divided by 2 minus k over delta x, okay, as we multiply by phi sub l, okay, plus our coefficient for ourself, so this is 2k over delta x, phi c, okay, plus u divided by 2 minus k over delta x, phi sub r, okay, and all this is equal to q at xc times delta x, okay. And so this equation right here, we'll box this guy. This is our finite volume equation for convection diffusion problems in 1D, okay. So if you have an interior cell, you can basically just apply this equation straight up, and then this will help you get the coefficients for the left neighbor, yourself, and then also for your right neighbor. Okay, so that's our FEM equation for 1D convection diffusion. Okay, so before we can use this, we have to do the boundary conditions. But after we do the boundary conditions, then we can do this for an example. But probably the example will have to wait till next time. Okay. Any questions on this? I think I'll probably start a new board for the boundary conditions. Okay. Okay, so let's do boundary conditions. So just like before, we have two types of boundary conditions. We have Dirichlet and we have Neumann. So let's start with Dirichlet boundary conditions. Okay. And just like we saw with the finite volume problems for diffusion, what we'll see here is kind of the same thing, where instead of becoming its own equation, what's going to happen is that these boundary conditions, they're going to modify our previous equation. Okay. And remember, depending on if the boundary conditions are on the left or the right, the modifications are going to be slightly different, in terms of the signs. So make sure you're kind of familiar with this process. So if you have boundary conditions in a location that you're not sure of, you can go from the equations from scratch. Okay. So for just an example, let's consider a Dirichlet boundary condition on the left. Okay. So let's say that we have a situation like this. So our cell in question is given by phi sub c, just like before. I've boxed it there. And on its left side, we have a prescribed value. So this phi naught right here, this is our Dirichlet value. Okay. And on the right, we have a standard, right neighbor right there. Okay. So let's go ahead and write out our finite volume equation. So our finite volume equation looks like this. So we have U times phi at xr minus phi at xl minus k d phi dx at xr minus d phi dx at xl is equal to q at xc delta x. Okay. Okay. And so the presence of the Dirichlet condition on the left side is going to modify some of these values. So we can't just use this the same central scheme that we did before. So basically, anything that has an XL, we're going to modify it according to the Dirichlet condition. Okay. So that means we're going to modify this term, and we're going to modify this. Okay. But all the terms of XR, those are going to be the same as before. So we're going to plug in basically the same things. Okay? So the modifications that we're going to make is that phi at XL, remember this represents the value of our solution at the left face. So in the case of a Dirichlet condition, we know exactly what that is. So phi at XL is just going to be phi naught. So we're going to plug that in for phi of XL there. Okay. And then d phi dx at xl, we're going to replace that with the derivative that takes the Dirichlet into account. Okay, so this is going to be phi c minus phi naught all over delta x divided by 2. Okay, remember we do delta x divided by 2 because we're only moving that half distance from the center of the cell over to that boundary. Okay, so then if we plug all that in and then we use the same expressions for phi of xr and d phi dx at xr, we get the following. We get u times phi r plus phi c all divided by 2. Let me clean that up a bit. Okay. Minus phi at xl, but since we know phi at xl is just going to be phi naught, so we're going to just plug in phi naught here. Okay. Minus k times d phi dx at xr, so that's going to be the same as before, so that's phi r minus phi c all over delta x. Okay, minus d phi dx at xl, so we're going to plug in our modified expression up there. Okay, and on the right hand side will still be the same, so I don't have enough room, so I'm just going to draw that arrow down there. Okay. So let's go ahead and rearrange the terms. And remember, everything that has x naught, we can go ahead and move that to the right-hand side because those guys are known, right? Because remember, our usual convention is that things that are unknown, we keep on the left, and things that are known, we put on the right, okay? So if we do that and we rearrange all the coefficients, we get the following. So we get u over 2 plus 3k all over delta x. Okay. This is a 3 times phi sub c plus u over 2 minus k all over delta x phi sub r is equal to q at xc delta x plus u phi naught plus 2k phi naught all over delta x.
Professor, I don't get it.
Uh-huh.
I don't get it.
Okay. So are there any questions on this?
I think that was a spammer.
I'm
I
positive that was a
think you
spammer.
just got Zoom bombed.
Yeah.
It should have been like, I don't get your mom. No, I'm just kidding. No, don't do that.
Yeah. No, the best way is just to deal with them as kind of quickly and quietly as possible. Yeah. Okay, so with these, when you're doing boundary conditions with convection and diffusion, you have to be really careful because the signs for the terms on the right-hand side, these can be different depending on if your boundary conditions on the left and the right. So make sure that when you're developing the equations for finite volumes for boundary conditions, make sure that you make sure you get those signs correct. So make sure you're kind of familiar with this process of going through the equations and doing this. So just so that you get the correct signs. Okay. Okay. So that's Dirichlet conditions. Okay. So now let's do Neumann conditions.
Professor, does the sign convection follow the same rules as last time?
So I think for the diffusion term, they should follow the same convention, but for the convection term, you have to be careful with that. So you want to make sure that you either have a positive u phi or a minus u phi on the right-hand side. So that part you have to be careful. But the diffusion term, the 2k phi naught all over delta x, then that I think that term should still have the same. That should have the same convention as before.
Okay, thank you.
Mm-hmm. Okay, so now let's do Neumann conditions. So Neumann conditions we're going to do them a little bit differently, and I'll kind of explain what that is. So let's kind of draw a characteristic case first. Okay, so we have our normal phi sub c. Okay. And then here we have a Neumann condition, but I'm going to define it a little bit differently. So let's say that on the right-hand side, our Neumann condition is our flux is going to be equal to gamma. Okay, and I'll kind of explain why I do it like that. Okay, okay. So let's write out the equations for phi sub c, just like before. Okay, all right. But I'm going to rearrange the terms a little bit. So I'm going to have it so that I'm going to group the kind of all the terms that involve phi at x sub r, and I'm going to group all the terms with phi at x sub l. Okay. Right, so we're going to have u at phi at x r minus k d phi dx at x sub r minus u at phi x sub l minus k d phi dx at x sub l, okay, is equal to q at xc delta x. Okay. Okay. So the reason I kind of wrote it at as flux is equal to gamma right there, just to kind of make things kind of simple for us when we evaluate this. So when I say flux, what I mean is kind of this combination of convection and diffusion. Right? Because up to this point, we've defined kind of our Neumann conditions to be the derivative of the solution at our boundary. But just to kind of make things simpler here, I'm going to define flux to be that. So to apply this condition, what we're going to do is we're going to replace this entire guy right here with gamma. Okay. All right. So if we do that, and we kind of rearrange the terms, just so we're kind of out of time, so I'm just going to skip to the end. Okay. So if we replace that entire expression with gamma, and then for these guys, we use our usual expression for an interior node because we have a left neighbor. We're given the following expressions. We have minus u divided by 2 minus k all over delta x times phi sub L plus minus u over 2 plus k all over delta x times phi sub c is equal to q at xc times delta x minus gamma. Okay. So that's the equation that results from a Neumann condition on the right, where basically I replace that entire highlighted portion with gamma. Okay. So from now on, basically until, you know, just for finite volumes, when I say a Neumann condition, that's going to be defined as the flux. So that's going to be the combination of both convection and diffusion, just so we can kind of wipe out that entire term right there. Okay, so we're out of time. So when we pick this up on Monday, we're going to go over an example. So I will see you guys on Monday, but I'll stick around if there are kind of any questions on this or just any questions that that I can take kind of, you know, privately. Okay. So have a great weekend, everyone. Stay safe, stay healthy, and you know, let me know if you have any questions on anything. Okay. I'll see you guys later.
Have a good weekend, Professor.
Thanks. You too, Rick.
Professor, I got a question
Sure.
before you take off. If we were doing a Newman boundary condition to the left, does that equation change?
Yeah, it does change. So if we had a Neumann condition on the left, then we're not going to replace the green highlighted portion. We're going to replace this red one here, okay? And so because we have this minus sign right here, so then, if I can change the color, actually we can keep red, it's okay. Oh my. So then because we have that minus sign there, this minus will become a plus right there. Yeah, so you have to be really careful about the signs here, because you know, you have different signs, you know, kind of floating around with all the different integrals. You want to make sure that, you know, you apply the correct signs to the right places.
Okay. But just to be safe, we could go back to that first equation that you have there and then plug it in and work it out.
Yeah. So for finite volumes, I think you know, until you kind of get the hang of it, that's kind of the safest thing to do is, you know, when you have boundary conditions, just go off kind of the starting equation and then plug it in and then kind of work through the math from there.
Okay. Thank you.
Yep.
All right. Have a good weekend.
Thanks. You too. All right, you guys, oh, okay. Okay, so I'm gonna sign off because I have another lecture coming up next, but if you have any questions, you can definitely email me and I'll get back to you as fast as I can, okay?